All right, so in this video I'm going to explain how we can take these Hessenberg matrices and do kind of simple matrix operations to them. Simple both in terms of the formula and conceptually what's going on, but also simple in terms of the computational cost required to basically transform this into an upper triangular matrix. And there's a number of reasons that we want to do this, but essentially we're going to be solving systems of equations involving these Hessenberg matrices that's almost upper triangular. We're going to use that fact to very simply get it into an upper triangular form, and then, once we have an upper triangular matrix, we can solve that relatively easy. Okay, and again, the other thing to keep in mind is that this matrix is going to be a much smaller matrix than the A matrix that we start with. So we're going to do a successive, a succession of matrix products. So we're going to multiply this by a succession of matrices. I'm going to call them, the first one is going to be omega 2. Let me just remind you that this matrix right here would be like an Hessenberg H5 matrix. So there are m plus 1, that's 6 columns and 6 rows. So we're going to multiply this, hold on one second, all the, let's see, omega 1, omega 2, omega 3, omega 4, omega 5. Okay, now what's going to happen, omega 1 is going to be, and I'm going to describe more precisely what's going to happen, but this is an overview of what's going to happen. Omega 1 is going to be a matrix that is going to cause this row, or this column right here, to just have an entry there and zeros underneath it. Then we're going to do omega 1 times that. We're going to have a new matrix. Omega 2 is going to be a matrix that's going to operate on these two entries that basically makes this a 0 and makes that whatever it needs to be. So omega 2 times omega 1, this part of the matrix will be an upper triangular form. Then we're going to have omega 3. Omega 3 is going to be a matrix that operates on these two indices right here and does something similar to it. It's going to make it so that this is a 0 and that's going to be something else. And then we'll have a new matrix. Omega 4 is going to take care of these two entries, and omega 5 is going to take care of these two entries. And so at the end of it, if we have all of this product, the product of these omegas times this matrix here is going to give us an upper triangular matrix. Now, just describing it as I did is not enough to guarantee that it's going to have the properties that we need it to have, because it's not just enough to do something to this matrix to get it into upper triangular form. It needs to be something that's going to keep us in the realm of the problem that we're solving, and I'll say more about that as we go on. But that is sort of a very basic overview. And I realize because of the erasure, these green zeros might be a little bit hard to see, but these are all zeros here. All of these entries are equal to 0. Okay, so let's think about what omega 1 is going to be. So omega 1, again, we just want to think about it operating on these two indices here. So omega 1 is going to operate on these two indices, but it's also going to change everything after it. Now, omega 2 is going to operate on these two indices and change everything after it, but as we will see, it's going to leave these alone. So there's a way that we can sort of build this up. Anyways, if we look at omega 1, what we want is a matrix. I'm going to call it R1. I'm using R1 because this is going to be a rotation matrix. So R for rotation. So R1 is going to be a matrix that satisfies two properties. One, it's a 2x2 matrix, and when I do R1 on H11, H21, I want it to be, I'm going to call it the following. The top entry here is going to be H11 with a 1 here in the upper index, meaning I have done one of these omegas to it. And the bottom entry is going to be equal to 0. Okay, but because I need to preserve the Euclidean norms of things that's happening here, well, the other opportunity, or the other thing that I need to have happen is I need to have that the Euclidean norm H11, H21 needs to be the Euclidean norm of the output vector. Okay, so it's pretty clear what this entry has to be. This entry just has to be the Euclidean norm of what we started with. Okay, so this entry has to be the Euclidean norm of what we started with. Now, if it if that's all that we were doing, if that's the only change that we are making, just making a change to these two things right here, we could just, say the new H11 is going to be the Euclidean norm of these two and move on. But we really need a formula. We really need a matrix formula because we're going to have to apply it to the entire matrix. Okay. All right. So then, what we're going to do, a matrix that has such a property where it preserves the norms is called an orthogonal matrix or a rotational matrix. And notice this is just happening in 2 dimensions. And so what we have happening then are what is called plane rotations. That is, rotations in a plane. And you might remember from linear algebra that these are given by the following formula. C1 S1 minus S1 C1. And the notation C and S, again, hopefully you remember from linear algebra, these are going to be cosine and sine. So C1 is going to be cosine of the angle of rotation, and S1 is going to be the sine of the angle of rotation, if you want to view things geometrically. It's not completely necessary for what we're going to be doing. So for us, what we want to have is we want to have C1 being equal to H11. So just in this simple setup that we have here for the first one, C1 is going to be H11 divided by the magnitude. We're going to have H11 squared plus H21 squared. And then S1 is going to be H21 divided by the square root of H11 squared plus H21 squared, like that. And so we're going to form our matrix R1 in this form right here, where C1 and S1 are given by that formula. Okay, that's not omega 1. So R1 is a 2 by 2 matrix. I'm going to embed R1 in a larger matrix with the proper dimensions. In fact, I'm going to embed it sort of in an m plus 1 by m plus 1 matrix. And so omega 1 is going to be equal to R1 here. And then we're going to have 1s along the diagonal, and there are going to be m minus 1 1s along the diagonal. This is a 2 by 2 matrix. So overall, if R1 is this 2 by 2 matrix, if it was the identity matrix, this whole thing would be the m plus 1 by m plus 1 identity matrix. But instead, it's R1 with the 1s here. So this block is an m by 1 by n by 1 identity matrix, and then the top 2 by 2 matrix is going to be given by this formula here. So that's omega 1. That's what omega 1 is going to be. When I multiply omega 1 by this matrix, every entry in this matrix is going to be affected by omega 1. Or all of the columns in the matrix, I should say, are going to be affected by omega 1. Okay, so that's omega 1. So let's imagine that I have done omega 1. So I'm going to erase this because I'm going to imagine that I've done it. So I've done omega 1. Now all of the entries in the matrix have changed a little bit. So this is going to be equal to 0. I'm going to put a 1 here to denote that we have done one rotation to it, or one of these omega operations to it. Okay, so maybe as you watch me writing one superscript, you can just watch this on double time or just fast forward until you see that I'm done. maybe you just really like the sound of this fine chalk on this fine chalkboard. Okay, so now what I have here is omega 1 times the original thing. Okay, good. So let's erase this. Now let's think about what R2 should be. So R2, again, it's going to have the same rotation form of the matrix before, with C2, S2, minus S2, and C2. And I'm going to write the formulas for the S's and C's down here. Okay, and so now the formulas are going to be the following. Yeah, okay. So now the formulas are going to be the following. Let's see here. Sorry, got to find the right page on my notes. Okay, I don't want to try to have to rederive it here again. Okay, C2 is going to be equal to H2. C2 is going to be equal to H32. And now, as we will see, in general, this entry really won't be affected by the omega 1 matrix, but because I don't want to go through and explain which ones will and which one won't, and it doesn't really matter to what we're doing, we're going to have it with the 1 here. So we're going to have H32, 1. And then we're going to divide by the magnitude. So again, what I need to do is I need to make a matrix that's going to rotate these two vectors here. Rotate, if I think about that as being like one vector, rotate that so that it is just a 0 here, and then up there is going to be a non-zero. It's going to be the magnitude of that vector, as we've seen before. Okay. And so in the bottom, we're going to have H32, 1 squared, plus H22, 1 here squared. That's going to be C2. And then S2, well, it's going to be very similar. It's going to be H22 in the top. Now, this entry will definitely be affected by omega 1, but again, doesn't matter for what we're doing. We're just going to put that superscript of 1 on all of them, since potentially they will all change, but only in reality a few of them will change. Okay, and then we're going to have the same bottom. So H32, 1 squared, plus H22, 1 squared. Okay, and so by the way, verify that when you define C2 and S2 this way, and then do H22 here, and H32 here, then what you're going to get is going to be the square root of H22 1 squared plus H32 1 squared in the top entry and a 0 in that entry. Okay. Now, I'm going to erase this right here because I need this room. So what is the matrix omega 2 going to look like? So omega 2, we're going to have a 1, then we're going to have R2, and then we're going to have 1s going down here. So here, this is 1, 1. There are m minus 2 1s. So again, a total of m minus 1 1s, just like we had before. Okay, but notice what's going to happen here. When you do omega 2 times this matrix right here, or when you do omega 2 times the first column, when you do this first column over here, is just going to be multiplied by this part, because we're going to have zeros everywhere else. Okay, so what's going to happen then, again, because you have zeros here and the H11 there, the H11 is going to multiply by that, which is going to keep it as a 1, and then everything else that's non-zero and non-1s is going to be multiplied by zeros here. So in other words, after you apply omega 2, this H111 will stay the same. And this is going to be helpful for how we apply this practically in the middle of an iterative method, in the middle of one of these projection methods. But we'll talk about that exact implementation later this week during the lab. Okay, so anyways, what we're going to get is now this entry is going to be equal to 0. This entry is going to be a new entry, and all of these superscripts are going to be 2's. So this is going to be the last example that I'm showing you, so I'm not bothering erasing, I'm just writing it through. Okay. So now after we do all of these operations, after we multiply on the left by omega 1, then omega 2, then omega 3, then omega 4, then omega 5. The order and the direction there is very important. What we're going to end up with is a matrix, which is going to be, I'm going to call it Q5, and here I'm saying Q5 is equal to omega 5 all the way down to omega 1. We're going to have the matrix Q5 times H5. We're going to have zeros on the diagonal, like this. And so we're going to have an upper triangular matrix. Okay, now notice this is still an m by 1 by m matrix. Okay, so what have we done here? So we have, let's not forget what's going on. So we've got hm bar times ym. We have hm bar times ym is equal to beta E1. Well, let me back up a second. So we have in the GMRES method. Remember, we are minimizing hm bar ym minus beta. Whoops. Minus beta E1. Now, Q5, because Q5, what is Q5? Well, it's a product of each one of these omegas. Now, each one of these omegas has the following form. It's the identity, a rotation matrix, and then the identity. So it's like a rotation matrix embedded in the identity. But all of these are unitary. By the construction of Ri, all of these are unitary, meaning omega transpose omega is equal to the identity matrix. Okay, and that's because the main reason that's true, and you can verify this for yourself, is that each of these Ri's is a unitary matrix, meaning the columns are orthonormal. So another way to say this is that the columns are orthonormal. Now, the columns here and the columns there are definitely orthonormal to each other, and you can see pretty clearly that they're going to be orthonormal to the two columns that pass through this Ri block. And in the Ri block are the sines and cosines, and you can just verify directly that they are orthonormal. Anyways, what this tells us then, since each of these omegas is unitary, it means that Q5, their product, is also unitary. Again, you can just see this if you do Q5 transpose Q5. Well, what are you going to get? What's Q5 transpose? Q5 transpose is omega 1 transpose all the way up to omega 5 transpose, and then we're going to multiply it by Q5, which is just omega 5 all the way down to omega 1. And by unitary, that's equal to the identity matrix. Omega 4 transpose times omega 4 is equal to the identity matrix, and omega 1 transpose times omega 1 is also equal to the identity matrix. So in other words, Q5 transpose times Q5 is equal to the identity matrix. Okay, so why does that help us? Well, if you have an operation, a unitary operator, and you do Qx, Qy, well, notice what happens by the properties of the transpose, basically the definition of transpose. This is equal to Q transpose Qx y, which is equal to xy. So in other words, it preserves inner products. A unitary matrix preserves inner products. It preserves the angles. And this is exactly what we think about a rotation. Like a rotation should not change the angles between two things. It should just change, their position relative to the origin or something like that. Their angle relative to the origin. But if you have a rotation and two vectors are like this, the rotation should just move the vectors like that. It should not cause the vectors to be, doing like this. Okay, but if the inner product is preserved, since this norm is based on an inner product, it means the norm is preserved as well. So in other words, since the inner product can't see the orthogonal or the unitary transformation, unitary orthogonal, however you want to call it, transformation, the norm can't see it either. And so what it tells us then is that this problem here is the same as if I were to multiply in this matrix, or in the norm here, by Q5. But the solution to this is going to be the same as the solution to Q5 HM bar YM is equal to beta Q5 times E1. Now this right here is it's upper triangular, and this right here. Sorry, let me put there. Oh no, sorry, I don't need the norm bars. Sorry. So now I want to solve this system of equations. The solution to this system of equations is going to be the solution to this minimization problem. This is an upper triangular matrix. This is something that I can compute. I mean, Q5 times E1 is just going to be the first row of Q5, right? So this I can do pretty good at. So I can compute this pretty easily. And in fact, I'm going to go ahead for something that I want to do in just a moment. I'm going to call this beta. So Q5 E1, I'm just going to call, following the notation in the book, gamma 1 down to gamma 5. But remember, there are 6 entries, so gamma 6. Okay. Now, I've got this over here that I can compute this way. I've got an upper triangular matrix times ym is equal to that. The only thing to keep in mind is that there's a little bit of ambiguity here. Right now, the way that I have it written, ym has to be has to be a vector in m+1 dimensional space. Or sorry, ym is a vector in m-dimensional space. This right here is a m+1 by m dimensional matrix. Sorry, this matrix right here is m+1 by m. Okay, 6 by m. But notice what happens. The last row of this matrix is just equal to 0. So I need to basically delete the last row of that matrix, the last row of this matrix, and I need to therefore delete the last entry, this y6 here. And the system that I'm actually going to solve is going to be this system, Q5HM bar ym is equal to this. But from this matrix here, I'm going to remove the last row, okay? And from this vector here, I'm going to remove the last y6. Or sorry, I'm going to remove the last entry, gamma 6. And so I don't exactly know a great way to denote it other than to explain it. So the matrix that I'm going to be using is going to be this matrix with this row deleted times ym is going to be equal to this vector right here with the y6 deleted. Okay, now I'm going to leave this here because there's something really cool that happens. It's really cool and very helpful for us. So let's say ym star be the solution to this problem here, where again I've imagined where I'm deleting the last row. Okay, so let that be the solution. Notice what's going to happen if you do Q5. Now, if I go back to Q5 HM bar, where I'm including the bottom row here, and I do times ym, and I subtract off, ym star, and I subtract off gamma 1 all the way down to gamma 6, notice what's going to happen here. Ym star is defined so that if I just look at the top m rows of this matrix right here, times ym star is going to give me the vector gamma 1 down to gamma 5. And that is what it means for ym star to be a solution to this equation. Again, with the modification where I delete the last entry of this and the last row of that matrix. If I get the solution to that, by definition, if ym star is a solution to that, by definition, this matrix times ym star is going to equal this gamma vector, gamma 1, down to gamma 5. Okay, now what about the last entry? Well, the last entry of this matrix is zeros, so this is just going to be equal to 0 all the way down to 0 with gamma 6. Okay, but notice where this comes from. If we come back over here, we're going to have Q5 times this right here. But this difference is exactly what we have down over here. So this, if ym star is the solution vector, we're going to have 0, 0, minus gamma 6. But this is just going to be equal to this because the Q5 is unitary. So this is going to be 0, 0, minus gamma 6. But remember, this comes because this is the minimization of B minus A xm, where we're saying xm is in the space km. Xm is equal to x naught plus delta, and delta is in the space km. So in other words, the norm of this vector is the norm of the residual. So in other words, gamma 6, the absolute value of gamma 6, is equal to the norm of the residual. So B minus A xn. Okay, so why is this helpful? So what this tells us then, so we can apply this either in the GMRES method or in the FOM method. The same procedure is going to work because remember, the GMRES and FOM are doing different things, but you still have to solve a system of equations where the matrix is HM, and so you can still do this this sequence of rotations called Givens rotations to transform HM into upper triangular in either method. So think about like in the FOM method, for example. What this is saying is that we can compute the residual without actually having to solve the system. Okay, because remember, even in the FOM method, we can compute the residual without computing A times xm from that formula that we got, but that formula involves the last entry of the right-hand side vector. But this is the last entry of the right-hand side vector. So in other words, if we go through this process of Givens rotations, we have accomplished two things. One, we have a much easier system to solve when we finally do solve it, and two, as a free consequence of that, this isn't our main motivation for doing this, but as a consequence of that, we get this free, not estimate, but exact formula for the residual without actually having to solve the system. So remember, in the question that I brought up for the FOM method, how do we choose M? We can basically keep doing this method over and over again, increasing M each time until this right here is less than the value that we want it to be, less than whatever tolerance we want it to be. Then at that point, we can solve the system. And we're in a very good position to solve this system because now we have an upper triangular system that we're solving. Okay, so think through the mathematics of this, and then on the lab day, I'm going to show you, hopefully, if I have enough time, a practical way that we can implement this. Now, that's not going to be a main focus of this week's, but it is something that I want to bring up because it is an important practical piece to this solution method. Anyways, that's going to be it for the lecture videos this week. The next set of videos I make will be later this week, and it will be the lab videos.